Hi everyone, welcome back to our YouTube channel here at The Construct, Becoming a ROS Developer. My name is Rodrigo, and like always, I have here one of our students. His name is Thien. He's going to be showing us what he did for his project, which is ROS Basics in C++, right, Thien?
All right.
Yeah. All right. So whenever you're ready, you can start showing your screen and talking to us a little bit about your project.
Yeah, I'm sharing my screen, I think, right now. Sorry for
Yes,
some noise in the background, perhaps.
we can see it. There's a little bit of, I think you have a vertical screen. Is that correct?
Yes, because I found that when I have vertical screen, I can separate three views like this for coding, for the terminal, and also for the live
Oh, that's
robot.
great. However, let me just make it a little bit. Do you mind trying to do it landscape? That's because when you're sharing your screen, it just looks strange in the video feed. So it's really small in my video feed.
Yeah, of course. So please wait for me for
Yeah, no
just
problem.
a
Sorry,
sec. I
I
will
know
to
it's more comfortable
rotate
like that.
display. Da, da, da. Rotate landscape. Have to make
That
something
looks so
over.
much better. Yes, that looks great. It's just a matter
Check.
of our YouTube settings here, so that looks good.
I will check my terminals. Okay, that's
Perfect.
still alive. Perfect. So
All right.
I have the coding here.
All right, go ahead whenever you're ready.
Okay. So
So
should I launch
the
the
first thing
code
that you're
right
going to
now?
do then is you're connected to the robot, right? Correct? Yes.
Yes.
And you're going to be showing us the main program that you had to do for this project. It's going to be your main launch file.
Yeah, so I have three nodes here, the file one node, the follow one node, and the auto record node.
Okay.
The follow one node should be the main launch file that will call the file one node and also the auto record.
Great.
So inside the follow one node here, I'm implement the algorithm to control the robot that should follow the one. And it called also a auto record action server to record automatically the odometry information of the robot while moving. It will call also a service called file one server to reposition the robot toward the one and move the robot next to the one so that the robot can be ready up next to follow the one maneuver.
Okay.
And yeah, so should I launch a demo and
Yes,
then after that
let's see what the actual robot does with this program.
yeah, so I pre-compiled the code already 5 minutes ago. So right now we'll call the follow one node, and inside the follow one node, I have a launch file here that will launch the Odom record action server, and it will launch also the file one server as a service server.
Okay, great, great. So then it's the three main parts um, coming out of this launch file. Great.
Yeah. So we have Odom record node that will start a action server. So the first thing is the main node here, the follow one node, it will call a service server that will reposition the robot and get the robot toward the one. and ready for the next one following maneuver.
So
And now,
at this point, the service server is done, and now the main program is.
yeah, and I'm showing here some information that I use for my I use to control the robot,
Oh, can you
like
explain
cross
that?
track error.
Okay, great.
Cross track error, it will calculate the distance between the robot center and the one. The curvature K here is the curvature of the trajectory that the robot is actually following. The heading here will calculate the angle that the robot is that will tell us how the robot is repositioning toward the wall. If it is 0, the robot is perfectly parallel to the wall.
Oh, okay.
Yeah, and the error here is the cross-track error here. And actually, I put in my code here a reference trajectory that the robot should be 25 centimeter from the wall. I have the desired cross-track error here at 25 centimeter, and the error here will calculate, will subtract the actual cross-track error and the desired cross-track error. And as we see right now, when the robot has finished a loop, it's stopped the odom recording, and it stopped also the moving automatically. And the action server is still running. The finding one service is still running, but the robot is stopped right now. So we have a clean ASIS if,
So did a clean loop around. Nice, great. And I can see at the bottom there that says that the autumn record was succeeded. So I'm assuming that's the last thing.
Yeah, so when the autumn record has finished, it will push back the result into a vector of the point that the robot has moved. Each 1 second, it will publish a new result into this vector.
Great. So, all right. So it seems like it does everything perfectly. So you mind just going a little bit deeper into the code so we can see how you're doing that? Could you make this the IDE? Could you maximize it so we can see the whole screen and it's easier for us to see?
Yeah.
Yeah, like that. Thank you.
Also, I will have a
perfect.
a slide
Great.
next to.
Yeah, that's perfect. Good.
Yeah. So I will minimize the window. So I will go from the problem statement. Just by sec. Okay. Now I'm in the one follower project for the C++, and the problem that we have is to got some ROS topic, subscriber topic, publisher, action server, and service server to do two motion mission. First thing, we need to assume that the robot will use the laser scan to sense around it, and when it sees something, it will assume that that's the one. And the first thing we have to do in the motion is that we have to reposition the robot toward the one, and we get the robot moved next to the one. The second motion mission that we have to do when the robot is next to the one, it has to follow the one on the robot right side. During the robot maneuvering, we have to log the odometry information and so for further investigation and other purpose. So we have sensing, laser scan, we have logging, odometry information, we have motion, two kind of motion that we have to realize. find the one and go to next to the one. Second thing, follow the one on the right side. The laser scan that we have has 720 rays from 0 degree to 360 degrees. So each 0.5 degree, we have a laser scan. So I came to the solution as proposed in the projects, and I separate them into 3 ROS nodes. The first thing is the file one server. Is a node to launch a service server that will have the robot to find the one, rotate toward the one, and then reposition almost parallel to the one. Not exactly parallel, just 45 degrees toward the one.
Yeah, I noticed that.
The odometry node, sorry for the mistake here. The odometry node is a action server. When called from the main node here, the follower node, it will launch. It will record the odometry information each point 1 second for 1 point. My main node is the follower node that firstly, when I start this node, it will call the file one server that help the robot to move next to the one and reposition and ready for the next maneuver. It will call equally the odometry core to start the recording of the robot position during the maneuver. I add something here. When the robot has finished a loop, it stops the moving action, and also it will stop the odometry core node and push back on the information it has collected during the maneuver into the result vector.
All right.
So next thing, I will go to the detail of each node here, the file one server, the follow one node here, and the odometry core node here. So the file one server, it will have to do 3 maneuver. Like firstly, it will read the laser scan and assuming that the nearest thing to the robot will be the one. So we do not have really visual perception here. We use just laser scan and we assume that the one is something near it to the one. And when it detects something, it will rotate toward the thing detected, assuming the one here. So we have the ray 360 here is the hitting of the robot. So it will rotate until the ray 360 is the minimum amount the laser scan. And when it did it, it will move the robot toward the object, assuming the one, until the ray 360 is smaller than 30 centimeters. And when it did finish the rotation and the go forward the one maneuver, it will rotate a little bit more to get the robot somehow as 45 degrees toward the wall. This is to make easier the next action of the one that of the robot that the robot have to follow the one.
Oh, I see.
The second node that we have here is perhaps the first node here, the file one server. Yeah, in the service server here for the one finding, we make subscription to the topic called scan. This topic receive information from the laser scan. Yeah, so convex file one, convex laser scan. Yeah, when it receives a new laser scan, it will push back the result into a vector, a that called scan range, and we will calculate the minimum. Where is the minimum ray here?
Okay, okay.
Yeah, here's the to do the maneuver. Okay, I will move next to the action server that do the odometry core. So I got the odometry core action server as an object to make easier the code and make the code cleaner, object-oriented design.
Mm-hmm.
So what the action server do here, it will make a subscription to the odom node that receive the information from the odometer of the robot. And each time it receives a new information of odometry, it will calculate the step, the distance, how the robot has moved, and uh, I have a rect sleep here to make the robot sleep to make the process sleep for 1 second. I just want to have a one point uh, one calculation in 1 second.
Mm-hmm.
I don't
So it
want
does it every
to,
second. Okay.
yeah. So I
You have
calculate the
10
distance
minutes, by
between
the way.
2 points. Yeah. Okay. So and in this odom recollection server here, I will make an assumption that when the robot has moved more than 5 meters, because I know the dimension of the area here. So
Right.
5 meters should be something reasonable that the robot had must make a loop.
Mm-hmm.
And I compare the initial position here, the start position, with the current position if it's inside a 20-meter circle. I call that it detect a loop.
And
So
in
when,
addition to more than 5 meters,
yeah,
right?
I have two conditions.
Okay.
Yeah,
So if
and
you wanted
when
two
the
laps, you would just do like 10 meters or something in this with this
yeah,
logic.
it could be, but I just want to be one lap.
Yeah, yeah, yeah. All right, I understand. Nice.
And after that, I move back to the main node here called the one following node. So in this node, it's makes subscription to the scan, it's makes subscription to, and it will publish to the command van here to command the robot linear speed and the rotational speed. Yeah, and this node, it will call uh, the action server that will record the odometry
Mm-hmm.
information, and it will call a service server that make the robot to move toward the one in the first time. And when the robot has, when the service has the fighting one service has been terminated, the robot is considered as considered that it's ready to move to follow the one.
Nice.
Okay, and yeah, the interesting thing here is I try to make two kind of control. I have the first model of control that I use linear PID to control the cross-check error. I will explain error later.
Mm-hmm.
I have the second method to control by a non-linear Stanley controller that control the cross-check error and the hidden error at the same time. So we have better positioning of the robot while following the one.
Oh,
Yeah,
nice.
to make the control and modeling, I kind of calculate the cross-check error here, D, between the robot and the one, and I choose the ray 180, the ray on the right side of the robot,
Uh-huh.
and I choose another ray ray A here at a theta angle from the right side. Yeah, in the chord is a 45 degree. So when I have the distance measure A and B here, I can calculate the cross-track error, the distance between the robot and the wall. And with A and B here, and assuming that the one is a straight line, I can calculate the alpha here, the hidden error. And with the hidden error and the cross-track error, I can control the robot position during the maneuver.
Wow, that's really nice. Um,
Yeah.
all right.
And the second thing here, when I try to control the two-wheel robot, I find that it's better that perhaps then actually I will control in the end the two-wheel robot, but in the meantime, in the middle of my code, I will control a virtual four-wheel a car-like robot. So I have the steering here, I have the speed here to control. Yeah, and I reuse much of material that using in autonomous driving, how to control a car.
Mm-hmm.
Then in the end, I will model the steering here and the speed of the car to actually control a two-wheel robot. So I have a virtual bicycle model to control by my TAD or Stanley model. And when I calculate the steering and the speed that I have to control this car, I will use some kind of geometric modeling to recalculate how much of angular and linear speed that I have to send to the two-wheel robot.
I see.
Yeah, so the thing here, when I calculate the cross-check error, the hitting error here, I I will calculate the yaw rate, how the robot should rotate, and yeah, after that is the steering angle or the turning radius and something that, and I change to the really in the end the real two-wheel model
Uh-huh.
here, angular and linear speed.
All right.
So actually, yeah, and I found in the internet some kind of the figure that I have the real the wheelbase, the geometry of the Turtlebot burger that I used to model here all of the thing.
Uh-huh.
And the advantage of this method here that I have more flexibility because when I model with the car model here, I can really model the wheelbase here. I can choose the wheelbase virtual that I want. I have some degree of flexibility while modeling my controller.
Right.
Yeah,
Nice.
path modeling. Yeah, yeah. In the end, yeah, that's just something to remember here. I
Mm-hmm.
calculate the cross-check error, and I have a desired cross-check error that is 25 centimeter that the robot should separate from the wall. And I calculate the error between the actual cross-check error here and what I want the design.
Right.
That's the desire. That's fixed to 25 centimeter. Yeah, so we came to the end. We come to the end right now. So for the motion control, first thing that I try here, I use that previously we saw on the real robot here. I use a linear PID controller. So here, the input to the controller that I use is just the cross-check error. So I take 25 centimeter. That's what I want,
And that's
and
it.
subtract. Yeah, yeah, that's desired cross-track error 25, and cross-track error here is the actual position of the robot. And then I tune a PID controller here. Yeah, I have some KE interval, some kind of interval coefficient here to keep the robot a little bit more further than what I want. That to have a balance between the proportional and the interval controller that will help the robot more stable. As we saw in the real robot maneuver, the robot move really fast.
Mm-hmm.
The second method, the the drawback of this method here, I control just only the cross-check error, so I don't care about the hitting. So sometimes the robot the robot is not really parallel to the wall.
Oh, okay.
But by controlling the cross-check error, somehow the robot is parallel indirectly by this, because if the robot is not in the desired cross-check error, we have to reposition the hitting of the robot. So somehow it can control indirectly the hitting error. The second method I try is use the Stanley method. That I find really, this is brilliant, that yeah, you can find on the internet the model, the real model that you on the dock bar. So the Stanley use cross-check error and heading error to control the steering of the robot.
Okay. And did you find a difference between these two? Is there a reason why you tried to? So you have two methods.
Unfortunately, yeah. So unfortunately, I thought in my mind that the second method with the Stanley would be more stable, would be more robust. But in the end, in the real robot, it makes more oscillation.
Oh, okay.
Yeah, and I think that because here in the Stanley method, it controls the hitting and the cross-check error in the same time, but our laser scan will have some noise, and I did not have filtering on the laser scan, and it will make the robot really sensible to the noise of the laser scan, and also to some error during the maneuver. And the linear PID method here, classical method that work pretty well, because I have proportional coefficient here and have a integral coefficient here to keep the robot under the balance. Even we have some noise in the laser scan measuring.
All right.
Yeah, the thing that I think that is a little bit strange here is I try to control a two-wheel robot without directly control it. I control.
Right. That was my main question. You're done, by the way, right? Because I wanted to ask you some things. Or do you?
Yeah. Okay.
Yeah. So congratulations, Thien. It's a really, really nice project, and obviously, the star of the project is your controller here, and I just wanted to congratulate you and tell you that we haven't seen this so far in this project, so it's really nice to see. You obviously must have some background in control to implement this, and it's awesome to see to have it working. So great job in that. Let me see. Yeah, the thing I wanted to ask you is, could you go a little deeper into the reason why you turned that differential drive into the virtual bicycle? I understand this for your controller, but would there be an analogous thing for the differential drive, or what's? How did you come to decide to make this virtual vehicle model, and how did you know it was going to work when transferring it to the Turtlebot?
Yeah, the thing here is when I work with the two-wheel model here, I'm a little bit lazy. Sorry for that, but
oh, okay. So it's too.
In the beginning, I did not actually understand the common angular here. I did not understand what it stands for. I understand that it will control the rotational speed of the robot, but I don't know how is it related to the linear control here.
Okay.
So at the beginning, I start to control this robot without really real understand of the two-wheel differential driving robot.
Okay, but then you did this and it came out really, really well. So that's impressive.
Yeah, and after that, I realized that if in the controller, if we try to control something with the steering and the speed, like we control a car, it should be something more flexible that we can model we can implement, and we can enhance really the stability of the robot by modeling the wheelbase here. Because
Right.
this is a virtual model, so you can really modeling the wheelbase here. You can modeling some more uh, controller aspect with this model
Yeah.
rather than the differential driving.
Yeah, that's amazing, and you have a way to bridge between the two models, which I think is
Yeah,
great. Um,
and actually here, this is really interesting because in the beginning when I do the virtual bicycle model here, I did not really calculate the real equation here. I should imagine that the common angular here should be something. Uh,
oh, yeah.
I calculate the curvature of the chariot of the path that the robot have to follow. I just know the speed, and so I in the beginning I have the equation like this: uh, the curvature of the wheel, the curvature of the path, and the speed, and it works actually in the
Oh,
real robot. And the really the the right equation here, we have to multiply by the robot width here also. The
right. Yeah, of course. Between
the
between the wheels. Yeah.
Yeah, but I understand that uh, even I have a wrong equation, this work like a proportional gain
A
in the
PID.
PID controller. So it helped me also to model to have more stability also. So in fact, in the end, in the real similar in the real, I enter this W in the equation, but we can really model this W.
Without it.
mm, yeah,
I'm assuming it'd be more of a bigger deal if we had a bigger robot with a bigger distance. But
yeah.
since this is a small one, I'd say maybe that's why. But and I don't know if it would make a bigger difference if the wheels were really far apart. I'm sure it would.
It could have some effect, but I think that it's not really serious effect, just a minor effect.
Okay. Okay.
And here, like as we can model the wheelbase here, so and when we change the wheelbase modeling here, we can really change the behavior of the robot because the wheelbase will affect the turning radius here. So when we change the wheelbase here, the robot should could turn with more like aggressively or smoothly.
All right. Okay.
So I have some kind of modeling parameter that I have to control. I have to test and to try. I have
Right
the
to tune.
controller parameter also to tune.
So you can tune it. Yeah, I like it. Well, Tien, do you mind stopping sharing your screen so we can see our faces here?
Yeah,
Great. So again, congratulations, Tien. This is really exciting because again, this is the first time we've seen a student implement a controller like this, and it was really interesting to see and to see that it worked. And I really liked how you went about your solving the issues that you had. You said all that explanation you went into about the angular, you didn't really know what the angular velocity meant because you weren't sure about the differential drive uh, method and model, and then you decided to go with the other one and tune it so it worked, and to see how it actually works, and those like that distance between the wheels that you didn't have to put it. That's really interesting to see, and I'm really glad to see that work. And other than that, um, I think you did a great job. There's always room for improvement, but I think you got the meat of it, the main part of it correct. So congratulations, Tien.
thank you very much. And also, I found that the course is really well organized, and I really love the idea to make a remote lab that
Uh,
everyone in the world can control a real robot from 12,000 kilometers.
oh wow, that's really really far. Yeah, that's the point. That's the whole point of this, to offer this experience to people, because it's one thing to put it in gazebo and see what happens, but there's another one to see it in a robot, and especially with a controller that you built from scratch like yours, and to test it around and see what the real world translation of that is. So thank you for saying that. We did that for this reason precisely.
Thank
Um,
you.
all right, so there you have it, guys. A really nice introduction into PID controllers, I think, with this project. You can also find courses on control in our website. Of course, this is for ROS Basics, so here Tien went a little bit above and beyond, which I love to see, and it also adds a little bit of variety with these presentations, which I think just shows how much you can play with your project to make it as good as you want. So if you're watching this and you're taking our course, I encourage you to do the presentations here like Tien, so you can solidify your ROS learning. And Tien, again, thank you very much, and congratulations.
Yeah, thank you very much, the team, for the great course, free organization, and free help.
All right. Well, that's it for us, you guys. So we'll see you next time for our next presentation. And yeah, so we'll see you guys around. Bye bye.
Bye bye.
All right, Tien.